Hello guys, welcome to our channel Electronics. Today we are going to start a new chapter, that is Semiconductor and Diodes. So let's see what what is semiconductor. The PN junction diode is one of the semiconductor devices with two semiconductor materials in physical contact. One with excess of electrons, that is N type, and another is excess of holes, which is P type. The most important characteristics is its ability to allow the flow of current in only one direction. In the opposite direction, it offers very high resistance. Semiconductor diode find wide range of application in all phases of electronics like radios, TV, power supplies, and computers, etc. Let's see the classification of semiconductors. Semiconductors are classified as 1. Intrinsic semiconductor, that is pure semiconductors, and 2 is extrinsic semiconductors, that is known as impure semiconductors. So let's see first the intrinsic semiconductor. A pure semiconductor is called the intrinsic semiconductor. Intrinsic semiconductor behaves as an insulator in 0 degree Kelvin. But at room temperature, some of the valence band electrons acquire sufficient energy to enter the conduction band and forms free electrons. Under the influence of electric field, these electrons constitute electric current, and the missing electron in the valence band creates a hole. The current conduction semiconductor is the sum of currents due to electron hole. The Fermi level of intrinsic semiconductor lies middle of the conduction band and valence band. Electrons being negatively charged move from negative terminal of the battery to the positive terminal, and the hole moves just opposite direction. Let's see a picture of intrinsic semiconductor. So here you can see it is non-doped. See the other type of semiconductor, which is known as extrinsic semiconductor. Due to poor conduction at room temperature, the intrinsic semiconductor are not useful in electronic devices. Hence, the conduction capability should be increased, and this can be achieved by adding small amount of impurity to the intrinsic semiconductor. This process of adding impurities is known as doping. The amount of impurity is extremely like 1 to 2 atoms of impurity for 10 to the power 6 to 10 to the power 8 intrinsic atoms. Extrinsic semiconductors are classified into two types depending upon doping impurities, which is P-type containing excess holes and N-type, that is containing excess electrons. So let us understand a picture. So let us understand the extrinsic semiconductor better by a picture. So here you can see the atom is doped with a pentavalent atom, which is known as doping. So this is why the semiconductor is known as extrinsic semiconductor. So as we have discussed earlier, that extrinsic semiconductor are of two types. First one is P-type, which contains excess holes, and second one is N-type, which contains excess electrons. So first one is P-type semiconductor. A small amount of trivalent impurity such as aluminum or boron is added to the pure semiconductor or intrinsic semiconductor to get a P-type semiconductor. Trivalent impurity, when added to the intrinsic semiconductor, introduces a large number of holes in the valence band. These positively charged holes increase the conductivity of P-type semiconductor, as the number of holes is very much greater than the number of free electrons in a P-type material. So holes are termed as the majority carriers and electrons are called minority carriers in case of P-type of semiconductor. So let us understand by a picture. So as you can see here, a germanium atom is doped with a trivalent impurity atoms. So do remember this point very carefully, that in case of p type of semiconductor, the intrinsic semiconductor is doped with trivalent impurity. The next one is n-type semiconductor. So let's see what n-type semiconductor is. A small amount of pentavalent impurities such as phosphorus or antimony is added to the pure semiconductor or intrinsic semiconductor to get n-type semiconductor. The addition of pentavalent impurity increases the number of electrons in the conduction band, thereby increasing the conductivity of n-type semiconductor. As a result of doping, the number of free electrons for exceeds the number of holes in the n-type semiconductor. Electrons are called the majority carriers and holes are called the minority carriers in case of n types of semiconductor. So let us take a picture of n-type semiconductor for better understanding. So here you can see a pentavalent atom is doped with the intrinsic semiconductor or pure semiconductor. So do remember this point very carefully, that in case of n type of semiconductor, the intrinsic semiconductor is doped with pentavalent impurity. So this is the most important topic of the semiconductor diodes, that is Fermi level. So what is the definition of Fermi level? Let's see. Fermi level is the highest energy state that occupied by an electron in a material at absolute zero temperature. So let's see a picture. So as you can see here, that the middle of conduction and valence band, the Fermi level is lying for semiconductor, and for conductor the Fermi level is overlapped, or the conduction and valence band is overlapped. So this portion of between the conduction band and valence band is known as the band gap. This is the band gap, and here the conduction band and valence band is overlapped, so there is no band gap present. So let's see the definition of band gap. The difference in the energy between the valence band and conduction band of a solid material that consists of range of energy values forbidden to the electrons in the material. So this is known the band gap. So let's see what is the definition of conduction band and valence band. The valence band is the band of electrons or orbitals that electrons can jump out, moving from the conduction band when it is excited. The valence band is simply the outermost electron orbital of an atom of any specific material that electrons actually occupy. So this is the conduction band. Now let's see the band diagram. So first, intrinsic semiconductor. For intrinsic semiconductor, the Fermi level lies in between the conduction and valence band. As you can see here in the picture A, there is the Fermi level EA5 that is lying between the conduction band and valence band. This is conduction band CV, this is valence band VV. So as we know, the extrinsic semiconductor can be of two types. For p-type semiconductor, the Fermi level lies near the valence band. So in the picture C, the Fermi level lies near the valence band. This is the valence band. For n-type semiconductor, the Fermi level lies near the conduction band. The Fermi level lying near the conduction band. This is the conduction band. The next topic is the Fermi Dirac function. Fermi level. So Fe is the Fermi Dirac function, the probability that a particle will have energy E, that is Fe. The formula for a Fermi Dirac function is 1 by e to the power e minus ef by kt plus 1. So ef is the Fermi level. For low temperature, those the energy states below the Fermi level EF. The EF is the Fermi level, K is the Boltzmann constant, and T is the temperature. So as we can see here, the absolute 0 Kelvin, the Fermi level is lying in between the conduction and valence band. So when the temperature will increase, we can see here at the high temperatures, some of electrons can reach the conduction band and contribute the electric current. This is how the graph will look after increasing the temperature. That's it. So that's all for today. The semiconductor and that's part 1. Hope to see you in the next one.
That's all about it for today. Thanks for watching and keep listening for more updates. Don't forget to like, share and subscribe our channel Techtronix if you like this video and want more videos from us regarding any query about electronics. Thank you.